Good morning, everyone. I'm Kai, and today I will talk about parameterized recursive refinement types for fully automated verification. So we introduced the type system with parameterized recursive refinement types, which generalize refinement types for various properties. And this type system is suitable for fully automated verification. So we also proposed the type inference procedure, or in other words, program verification procedure. So let me give an overview with examples. So this is a program with 3 functions. And the function range takes an integer n and returns the reversed range from n to 1. And the function len takes a list and returns the length of the given list. And function main checks that the return value of range n has length n. And otherwise, it fails. So our goal is to verify such program will never fail. And in this case, so the length of range n is always n. So to verify such programs, we use refinement types. And for this example, we use the refinement type ilistl, which means the integer list of length L. So the new has length 0, so new has type ilistl of 0, and the singleton list has type ilistl of 1, and so on. And yeah, so this is the definition of ilistl. And new has type ilistl of 0, and const takes the list of length y and returns the list of length y plus 1. So once we give such definition, we can derive the types of expressions from this definition. So yeah, let's go back to the program. So using this type, the types of functions can be given. And so for function range, it takes the integer n and returns the list of length n. So new has type ilistl of 0, which is the same as the ilistl of n. And const, in the typing of const, the recursive call has type ilistl of n minus 1. So the whole type of const is ilistl of n. Yeah, it may be easy. So I'll skip len and explain main function. In main function, range n has type ilistl of n. So the length of range n has type integer n. So according to this type information, the both sides of comparison always has the same value. So they are always true. And we can prove that the program will never fail. Yeah, so in last example, we embedded the length information into the refinement types. But another program requires different information. In this case, this is the insertion sort, and we'd like to verify that the return value of insertion sort is ascending. So we have to embed the information of sortedness of this into refinement type. So in this case, this is the refinement type. Ilist S stands for the sorted integer list. And so look at the bottom line. So the lists of 7 and 5 cannot be typed with this type because it is not sorted. And yeah, look at the parameters of ilist S. The first is empty. And so nil is empty, nil is empty, and is empty is 1, which means true. And it is 0 otherwise. And for the second parameter is head. So it corresponds to the first element of the list. And in the case of nil, the second parameter is discarded. So this is the definition, and as before, we can derive the type of expression from the type of constructors. And the red part is the precondition of const, which means that if the second parameter is not empty, the first entry should be less than or equal to the second entry. Yeah. So this does not satisfy, cannot be typed with, does not satisfy this precondition, cannot be typed with this list S, which is the case for the list of 7 and 5. And so go back to the program, and this is the typing of functions. So in the main function, I thought my list returns list S of something. And yeah, as you can see in the type of is ascending only accepts the sorted list, and it always returns 1 in this program. So it can be typed as, like this. So is ascending of I sort my list always returns int 1. So this program will never fail. Yeah, this is also easy. So okay, so once we define the refinement type, which is suitable for each program, so we can verify program easily. However, the appropriate refinement types vary from program to program. So we have to find and provide appropriate refinement types. But how can we do that? So the one approach is to manually declare and annotate the appropriate refinement types. So, however, this depends on the knowledge of programmers and, well, programmers or those who want to verify the program. So we take another approach, which is the verifier automatically assigns appropriate types. So to do that, we introduce a general form of type called PRRT. And using this PRRT, the verifier infers types with reduction to formulas called CHCs. Okay, so we introduce a PRRTs, which is the generalized refinement types for various properties of recursive data structures. So, for example, for integer lists, the PRRT I list x is defined as this. So it is parameterized with an integer representing the arity and a function, a predicate, and another function. So if you see the green part, and this is a type of constructors, and this is similar to what I have explained before. So compared to these two instances, so as you can see, fnil and fconst is instantiated with the function returning 1 or 2 integers, and pconst is also instantiated. So if we instantiate functions and predicates properly, we can get specific refinement types representing some various properties. So using this PRRT, our type system is so expressive. So generally, PRRTs derived from parameterized data types. So data types are parameterized with the arity, predicates, and functions, which is what delta means. And in addition, delta is parameterized with integers. So there are two groups of parameters. First, predicates and functions, and then the dependent integer parameters. Okay, so this is the types of constructors, and well, the definition is a little complicated, but if you compare this with the 3 instances, you can see that it generalizes the refinement type constructors. Well, in this case, new and const is what I have explained before, and B-tree node stands for the binary tree node. So this refinement types is not only for lists, but also for more general data structures. And so this is a type system. Based on PRRTs, we introduced the type system. And this judgment takes two environments, C and gamma, and precondition phi, an expression E and the type tau. So this means that the expression E refers to a value of tau, a value of type tau, or diverges. So diverges means infinite group. So it cannot prove the termination, but it can prove that the execution of E does not fail. So I don't explain much, but I will explain only two key rules. So one is the typing rule of failure. So basically, failure cannot be typed because in this case, the execution of fail is always fails. But in this case, if precondition contradicts itself, it means that the expression fail is never reached. In that case, the expression fail can be typed. Okay, so, and this is another typing rule for match expressions. So the original rule was so complicated, so this is a specialized version for integer lists. And so match expression is at the bottom line, which means that if S is new, it executes E new. And if S is const, so it evaluates E const with x1 and x2. So if this expression has type tau, if we'd like to prove that this expression has type tau, so we have to prove both E new and E const have type tau. But when typing the E new, we can use more precondition for phi new. So because we know S is new, we can use F new and P new in preconditions. Okay, so of course we have more typing rules, but we stop that and explain. I explained that the soundness, the key rule, a key property of this type system. So first I'll explain this program type judgment. So a program D is typed, and in this case, gamma indicates the types of global functions in D. So this statement means that if a program D is typed, and in this case, main has this type, so precondition is true, then D is safe, which means D will never fail. So this means that the main accepts all arguments without failure. So the function main works for every values of arguments. Okay, so we can see that the program verification, we can see program verification as the type inference. And we also propose the type inference procedure to verify programs. So this is the entire structure of program verification or type inference. So first, we unify some parts of types, and then we instantiate the types, but only function part. And then we reduce the program to CHCs, which can be solved by the backend CHC solvers. And so it is satisfied. It means that type can be inferred. So the program is verified. And if it is not satisfied, it may mean that the value of instantiation of F is wrong. And so we retry instantiation of F. Okay, so the first step is the unification of deltas. Well, delta is something like iList X. And so we share, so the verifier share delta to reduce the number of predicates and functions to make the verification easy. So, for example, in this case, the return value of isort is ascending. So the return type of is isort, and the parameter type is ascending share the same delta. Well, you can see that those types have different refinement formula, phi2 and phi3. So this part can be different, but they must have the same delta 2. So the same predicates and functions. And in step 2, we pick the verifier picks the value of functions heuristically. So currently, we only use 9 simple small functions, but they can express some properties like the length or sortedness of lists. But yeah, for more general case, it may not be enough. So the better heuristics is left for future work. Okay, so let's see the example. The return type of isort includes delta2, which can be instantiated as this. Well, in this case, we use F1 plus and F3 plus. So in this way, we can instantiate the functions. But as you can see, the predicates are not instantiated and untouched. So in the next step, we will use this as predicate variables. So in step 3, we reduce the program to CHCs. So CHCs are extracted from the type derivation tree. So in this example, new has this long type, and so this type has 3 predicate variables, P1, P2, and PL. So using the constructor typing rule, we can extract 2 formulas, which includes predicate variables. And this is CHC. They are CHCs. So of course, from the other parts of type derivation tree, we can extract more CHCs. And once we obtain the CHCs, we can check the satisfiability with predicate variables. This is CHC solving, and the verifier uses the backend CHC solvers. And if they are satisfiable, as I've said, the program is proved to be safe. And otherwise, so the heuristics of F may be wrong. So we retry with mu N and F. Okay, so we have implemented the prototype verifier using this procedure. So we use Z3 and Hoist as the backend CHC solvers. And this is the result. So we could verify some challenging programs as small but challenging programs in a fully automated way. This includes the isort is sorted, which means the sortedness of the insertion sort algorithm. And we can also verify some programs of trees. So it means that our procedure not only for this, but also for other structures. However, we have failed to verify some other programs, including M-sort is sorted, which means the sortedness in the merge sort algorithm. And so to identify the cause, we tried the verification with manually declared functions. And it still failed, which means the heuristics for choosing functions is not the cause here. So the main cause is in CHC solvers. So to verify more programs with our approach, a more efficient CHC solver is desired. Okay, so I'll explain the related work. So there are many research using refinement types for program verification, but initially it needs the manual declaration of full type. And after that, there are some studies where some type information is inferred automatically. However, they still require some annotations for various properties. And so they are not fully automated. Yeah. Okay, so in conclusion, we have introduced the parameterized recursive refinement types, which generalize the refinement types for various properties. And so the type system based on it is suitable for fully automated verification. So we also propose the type inference or program verification procedure. And we obtained some promising experimental results. So yeah, okay, so, but we have something left. So future work includes improvement of CHC solvers and more better heuristics or functions. Yeah, thank you. Question?
Thanks for your talk. I was wondering if your technique could handle mutations in the data structure, or is it only for functional programs?
Sorry, I can
Can you handle side effects like can you mutate the lists in place, or can you handle only purely functional programs with your technique?
Excuse me, I couldn't. Could you speak more?
Yeah, so I was wondering if you can perform writes to the structure, or if you can only do things in a purely functional way, like in a Haskell-like language, or can you do some things like in-place modification like you will do in C?
Do you support mutation or side effects?
No, so I have, this is for the pure functional programs, and the mutation, the verification of programs including mutations a little difficult, and yeah, there are some research. You may be able to use refinement types, but the combination of this research is not what I have studied. So, there are more rooms. There are some. So I have. There are other things. I have to work more with more priority. So I don't think of mutation such things.
Okay, thanks.
Thank you.
Oh, yes.
Hello. Thanks for the talk. I was wondering if you could also express more like complex like predicates. For example, like if it's a balanced like tree algorithm, you could express something about like the balances of the tree, or is there like a limitation on what types of predicates that can be expressed with like refinement types automatically, apart from like sortedness and like size? Like, what is the logic behind that?
Sorry.
Oh, like what is the logic that the user can use in defining like the predicates?
Yeah, so it depends on CHC solvers, but basically, so theoretically any predicate can be done, but so in reality, maybe only something like linear integer arithmetic or something.
So I have a question for you, actually. So is this modular? Can you check like a single function in absence of the call site, or do you require like the whole program to be typed simultaneously?
So yeah. In this very research, it is whole program and not modularized. But I think it is easy to extend this for modular verification.
Let's thank the speaker.